record. Okay, so let me start at the beginning here of chapter 18, which is about order, chaos, and fractals. The starting point is a Hamilton, or sometimes called a Hamiltonian, system of n degrees of freedom. And it has n coordinates, which we typically call q, and n momenta, which we call p. And the time derivatives of q and p are given by, well, they're represented by dots. In physics departments, we frequently represent time derivatives just by a dot. So the time derivative of qi is the partial of the Hamiltonian with respect to the ith momentum pi, and the partial derivative of the momentum is of the ith momentum is minus the partial derivative of the Hamiltonian with respect to q sub I. The Hamiltonian.
Those don't have to be Cartesian, right? That could be like cylindrical or spherical coordinate systems, like anything.
Yeah, these are just arbitrary coordinates here. And then the Hamiltonian then is a function of them. In the simplest case, it's something like a quadratic, it's something like pi dot squared summed over I plus a potential energy that typically depends upon the q's and can be essentially arbitrary. So that's how that works. Let me see if I can connect. Oh, Christ, it's in the middle of a backup, so I better just leave it. I was going to connect the iPad, but maybe we don't need it, at least in the beginning. So since the time derivatives are given by partial derivatives of the Hamiltonian, the time derivative of some function of the q's and p's then is a sum of these terms, the partial derivative of the function f with respect to time. I should have had a comma t here, so let me write a note to myself. So there should be a comma t here, I think. Anyway, so it's the partial derivative of f with respect to time, and then the partial with respect to each of the q's times the time derivatives of the q's plus the partial derivative of f with respect to the p's, time derivative of the p's. And then if you substitute in Hamilton's equations, you get this structure here. And that structure is called a Poisson bracket. It's sometimes written with curly brackets, fancy parentheses. I chose to write it with ordinary square brackets because that's the way we write a commutator. And in quantum mechanics, the functions f and h become operators, and their Poisson brackets is replaced by their commutator divided by I h bar, where h is Planck's constant, h bar is Planck's constant divided by 2 pi, then we multiply by I. So the quantum mechanical version of this is that, well, the Poisson bracket part, this part here, is that this is the Poisson bracket. In quantum mechanics, it turns into the commutator of f with h divided by I h bar. And the commutator in quantum mechanics is just the product written in two different ways with a minus sign. So f times h minus h times f over I h bar. This is all, for those of us who have been living with quantum mechanics in my case, most of my life, in the students' cases for days, weeks, months, or years, after a while, this becomes just, standard stuff, and we don't even think about it. But I must imagine that I imagine how difficult and surprising this must have been to the people first inventing it. I remember reading a description of Dirac's description of how he came upon it. He was the first one to actually make this identification. The others were stumbling around it, but he said he went on a walk one night, and when he got back to his room or rooms at Cambridge, he went to the library, or he went to his library and looked up what the Poisson bracket was, and then asked himself whether the Poisson bracket of Q with P could be IH bar and so forth. And then when you generalize that to this arbitrary structure here, that the quantum mechanical time derivative is the commutator of the operators divided by IH bar, where F is some arbitrary function of the Q's and P's or whatever we're talking about, that's a huge leap. This then isn't really, well, anyway, it's a big change. Anyhow, to get back to the classical system, a Hamilton system with n symmetries. Now, I think we talked about symmetries a little bit in some of these chapters, but it's intuitive what a symmetry is. Typically we have translational and rotational symmetry, and we have symmetry under Lorentz transformations. And so a Hamilton system with n symmetries has n conserved quantities Ci. This was actually pointed out by a female physicist named Emmy Noether, back in the first half of the last century. I don't know when it was exactly. And that's true classically and quantum mechanically, although Higgs introduced a new wrinkle to this. That is to say, what's the symmetry of? Is it of the Hamiltonian? Is it of the action? Or is it of the vacuum? And I remember a long time ago, Sidney Coleman wrote a paper saying a symmetry of the vacuum is a symmetry of the world. And in fact, what Higgs showed was that if you had a symmetry of the action, but it wasn't a symmetry of the vacuum, then you could have something that was called then spontaneous symmetry breaking. Anyway, actually, one could even have a symmetry of the action and a symmetry of the world and still have a spontaneous symmetry breaking, but that's another story. Anyhow, a Hamilton system with n symmetries has n conserved quantities. Actually, I should check what I just said. It seemed right when I said it, but there's a little more detail that needs to be filled in. Anyway, if time translation invariance is one of the symmetries, and normally we say that's the case because the Hamiltonian is time independent, and so time translation is a symmetry of the Hamiltonian. And if the conserved quantities are, remember, we're talking about n conserved quantities, if they're also time dependent, then we say the system is autonomous. And the Hamiltonian is one of the conserved quantities. And well, let's see, this is a very long sentence. If time translation is one of the symmetries, and if the Hamiltonian and the conserved quantities are time independent, then we say the system is autonomous, and the Hamiltonian is one of the conserved quantities, and its Poisson brackets, which each of the conservative quantities vanishes. I don't know if anybody should write a sentence that long and complicated. If the conserved quantities have vanishing Poisson brackets, then they are said to be in involution. This is just a technical term. And an autonomous Hamilton system of degree n that has n independent conserved quantities that are in involution is Liouville integrable. And in principle, then one can integrate Hamilton's equations, in other words, these equations, for a system that has all these nice properties and is Liouville integrable. So an example of such a system is one that you've probably seen more than once. You might have n q's and n p's, but each q and p each q only talks to its own p and vice versa. So the Hamiltonian is the sum of n independent harmonic oscillators. And then the Hamilton's equations are q dot, well, it's the partial of h with respect to p, and so that's just pi over mi. And pi, on the other hand, is minus the partial of h with respect to qi. And so this is, this negative sign means the thing oscillates, and the energy of each oscillator is conserved, and it's just p squared plus q squared, essentially. And the coordinates of momenta then run over the surface of an n torus in a space of n, 2n dimensions.
What
Now
is
that,
the
yes,
sorry, what is the omega for? What quantity does that define?
that defines the frequency.
Oh, okay.
So it shows up this way. You see, the time derivative of q being p is really just a definition of p. This is p is equal to mv. Q being a conventionally is a position. Q dot then is a time derivative position, that's a velocity. mv is p. So this is really just a definition, this equation. The business equation is this one. And it says that the time derivative of the system is proportional to the square of omega. And it works out then that the coordinates are sine omega t, and the momenta go as cosine omega t. Of course, with the phase, you can interchange sines and cosines. Anyway, this is a very nice system that is one that we love because it's so simple. And in fact, it plays an enormous role in physics. You might think that when you've finished the first or second year of physics that you've put the harmonic oscillator to bed, never to see it again. But in fact, it rises in the middle of the night and comes back again and again and again. And in fact, in quantum field theory, in those quantum field theories that are exactly soluble, the fields, the Hamiltonians are just sums of harmonic oscillators, and the fields are just linear combinations of Q's and P's of harmonic oscillators. So
Can I ask a question about the Matlab that was in the picture right there?
Okay, direct me. Where do you, here?
Yeah, right there.
Okay,
So,
yeah, I'm going to get to this in a minute, but go ahead, ask your question.
Perfect, because I was kind of looking and it said that those functions aren't integratable. So are you looking at these functions as like how their derivatives move, or are you looking at it as like actual particles in movement? Because like in one of my classes, we can't always graph what a function is going to look like. So we can graph what its derivative versus time is going to look like, or we can graph what its double derivative versus time looks like. So I was just wondering, like, if these particular graphs are, or when you're looking at these, if you're looking at like their derivative functions rather than like the functions that you can integrate themselves.
Okay, well, of course, I'm a physicist rather than a mathematician. And so we basically avoid dealing with super awkward functions. We typically are dealing with functions that are smooth, and so you can essentially graph anything. That's kind of the attitude in the physics department. It's my attitude. When I was your age, I had the mathematical point of view, but with time, I've just, in other words, it doesn't mean that in physics we ignore such things, but it means we don't pay attention to them unless we have to. So to get back to the basic definitions, a Hamilton system is a rather nice system. It's a special system that has these special properties. And it's also it's a mathematical system that has these nice properties, can be converted into a quantum mechanical system rather naturally. I didn't really understand your question, so I can't quite answer it. I do best.
Well, because I was looking at these functions, like the q dot and the p dot.
Yeah.
And I was looking because like the coordinates in the momenta, you're able to map those, like you're able to graph those, right? And that's what that up there was, the q1, e1, those are coordinates. And I was just wondering like if those particular graphs were graphs of like the q dot and the p dot in Matlab.
Well, no, these are just graphs of Q and P. I could, I guess, rewrite the program to plot graphs of Q dot and P dot, but remember, P is essentially Q dot. So this is kind of a graph of Q and Q dot. And in fact, this is a harmonic oscillator. So it's so P is essentially Q dot. Let me just make sure this is the Hamiltonian 18.5. Okay, so this is a harmonic oscillator with some other terms that make it non-integrable. It still obeys Hamilton's equations, but you can't integrate it analytically. Instead, for this particular case, I pulled up, remember here, in fact, you guys might want to do this right now, since you're sitting in front of a computer. You could send a browser to GitHub or GitHub. I don't know. Do you know how people pronounce that? Is it GitHub or GitHub?
I say GitHub.
What do you say, Abby?
I feel like GitHub would be the right one.
All right, let's go with GitHub then. And 2 votes for GitHub. So github.com and then my first name, middle initial, last name, and then you get a page in which you have to, here, let me show you what happens if you do that, in fact. So let's click on that. It brings this up. You're now on GitHub. And if you click on repositories, you can pick these various repositories. And the one you want to pick for class today, of course, is the one that is Order, Chaos, and Fractals, the name of the chapter. And then you can look at all of these various possibilities. And one is coupled oscillators. So let me see, I think I've already got this one here. Is it? Yeah, this is, so this is the Matlab code that generated these pictures. And
did you send us that link?
you can get it. You just click to this thing. You click on this.
Oh, on the, okay, yeah.
click on, in fact, in every chapter, I mentioned that you can get the codes, either Fortran or C or Matlab or whatever. You can get it by going to this github.com and then my name. And then you have to sort of, click in the right place and you can get this thing. So in other words, what you have to click on here is you have to go to the different, what are they called? Repositories, the different repositories, and you have to go to this repository, and then you have to click on view code, and then you get a choice of all these different codes. Now for this particular ones, we're talking about harmonic oscillators. So you click on this one, and what, now I've got Matlab sitting here. In fact, I just downloaded the new version. You guys can do that also if you haven't already. The 2022A version of Mathematica is available, so you can download and install it. And this is the code for the van der Waals oscillator. What we could do is here, go to new script, and then I could just grab this thing. So it's, let's see, maybe I can do this. Whoops, no, this is sending a, well, all right, this is actually sending it. I can send you the script quite easily. Even though you can download it. So here's a way of getting it. But I was thinking of just grabbing it like this and then putting it here, and now changing the print statement so I don't screw up what I've already done. So I'm going to just put new here. I encourage you, by the way, to play with Matlab. This, I think the best attitude to take with regard to Matlab is just to sort of play with it. If instead you try to understand everything, well, I don't know, that might take forever. So let's see, I was thinking of making this different and faster. Let's suppose we made this a 10 and omega 2, maybe make that 20. Whoops. And let's see, I don't remember what lambda, oh, we want to increase the coupling. So let me make lambda stronger. Let me make lambda, I'll make lambda 3. And now suppose I run it and maybe we go for more steps. All right, let's suppose we do 200 and here 1,000. I'm a little worried about how long this will take because I don't, oh God. So what is this? This is HOS, I'll call it. Save. Okay, it's running. Oh, wow. So wow. All right, so these are the two figures. That's the first figure. So figure 1 changed into something quite different. And figure 2, I don't know where the hell figure 2 is. Let me see. No, I don't see any figure 2. Well, that's kind of amusing. You see the difference here. That figure one, well, this, I guess, is like, this is the generalization of that, but more steps and different values of the parameters. And I think we're getting into something like chaos here. And
could you briefly describe what, like on the sides, it kind of, I don't know, like it's almost like a wave function before it comes to that center point. It's really obvious in the one that you just did.
okay, what's your question again?
Like if you're coming from the sides going to the middle, horizontally, it looks like almost like a vortex and waves coming into the center. Yeah. What?
Yeah, I don't know what happened. I just moved my mouse and the thing changed.
But like in terms of the function, like what? Is there something specific?
This is the
causing that?
trajectory. You see, what happens here is that in this program, I'm telling Matlab to use ODE set, ordinary differential equation set, with an accuracy of 10 to the minus 11 and a tolerance of the same size. And then it's computing T and X as doing this ODE 45 is a MATLAB program that integrates these, it integrates this equation, the Hamilton's equation for this system. And what I had to do, I had to give it this function, which I called harm for harmonic.
So it's just integrating it numerically because, like,
Yeah. Oh,
analytical
absolutely.
solution.
Yeah, this stuff is not integrable. The term integrable means analytically integrable, and in fact, in that Liouville sense. Whereas over here, what I do is I tell it there's a function x prime and there's a function h, and it uses that and a function harm. And where did I say what? Let's see, I don't think we need all that. So there's harm, x prime is harm, and h is equal to Hamiltonian, and I defined these this way. So this is, I don't know, this is the way I played with MATLAB. I think MATLAB is actually designed to require less effort than I put into it. And in fact, one of you, I think Douglas, suggested using, or maybe it was Abby, I don't know, well, suggested using the simulations capacity of MATLAB. I wasn't doing that, but if one of you know how to do that, then fine, we could do that. But I actually just wrote the code and used this MATLAB program ODE set. Anyway, what it does is it integrates Hamilton's equations, and this is for two coupled oscillators in these rather simple, just m equals 1, and these two frequencies, this value of the coupling. And then the equation here, the Hamiltonian I chose was this, rather than the one that's trivial that you can do analytically. So, and just to illustrate how the fact that most systems are not integrable, you just take two integrating particles moving in empty three-dimensional space, but interacting with each other in some way. That's a system of 6 degrees of freedom, 7 conserved quantities, but oh, let me see, what am I saying here? That's the two-body problem. 6 degrees of freedom, 7 conserved quantities, it's integrable. And that's, for example, like the moon going around the earth or the earth going around the sun. But when you go to 3 interacting particles moving in empty space, you have 9 degrees of freedom, only 7 independent conserved quantities, and it's non-integrable. And that's just because it's non-integrable, it can't be done analytically. Of course, you never know, somebody might think of something clever and invent some new mathematics that works it out, but it's been an unsolved problem for hundreds of years. And but of course, it can be integrated like instantly by Matlab or any computer. So, but Hamilton systems are special. The 2n time derivatives satisfy not just Hamilton's equations, but as a consequence, they satisfy these special equations. And moreover, an integral of P1 dq1, Pn dqn over a closed trajectory in phase space turns out it's a time independent. It's time independent, and that's something that is called a Poincare invariant. By the way, the Poincare family was not only composed of mathematicians and physicists, but I think one of them became president of France. Whether he had anything to do with World War I don't know, but anyhow, I hope not. That was a disaster. So the idea here is that you have 3 trajectories. So one trajectory, another one slightly displaced, and a third one slightly displaced. And then you take the area, you get basically a triangle because you have 3 points at any given time, and you just follow those points, and the area is then independent of time. Anyhow, the point is, although Hamilton systems are special, few of them are integrable. And for example, 3-body problems insoluble. All right, let me get on to some other definitions. I defined autonomous earlier, and an autonomous system of n first-order ordinary differential equations. This is perhaps a different definition of autonomous. An autonomous system of n first-order ordinary differential equations looks like this. So x1 is f1 of all the x's, and then x2 dot is f2 of all the x's, and then xn dot, time derivative of xn, is fn of all the x's. And when you look at it at first, you'd say, well, this is a pretty damn simple system. That's pretty easy to integrate, and yeah, it is numerically. But it's actually even more general than it seems, because you see, you can take a non-autonomous system, one that has a time in it. The FIs all depend upon time. And then you just say time is xn plus 1. And you say fn plus 1 is equal to 1. And that gives you a system of n plus 1, that's an autonomous system of n plus 1 equations. So and moreover, if you have n higher order ordinary differential equations, ones in which you have x double dot here and x triple dot there, you can rewrite that as an autonomous first order system of more than n first order ordinary differential equations. And so as an example of that, we can look at the forced van der Pol oscillator. And what we have here is a second order time dependent differential equation. So y double dot plus this times y dot plus y is a sine omega t. So this is the forcing term, and the rest of this is the oscillator part. And to convert that into an autonomous system, you set x1 equal to y dot, x2 equal to y, and then you set x3 equal to t. Then x3 dot is obviously 1. That's why, that's this trick, fn plus 1 is equal to 1. So then you have an autonomous system of three first order ODEs, or ordinary differential equations. And this exhibits chaos for certain values of the parameters. And so I plotted a couple of them here. Let me see where some of this stuff seems to have gone away. Let's see. So this one is the ordinary oscillators. This is van der Pol, and what I did let me see, what did I do? Okay, so here are this is the van der Pol program that I wrote. And what we can do is we can bring it over here and then run it for for different values. In fact, I did that a little while ago, and what I'm puzzled about is I don't see where it is that I did that. So this is van der Pol. What is this one? Oh, this is just the whole set. So there's van der Pol, and there's the van der Pol. I brought it up as this, and I also ran it for new values. And so this is the van der Pol's oscillator. If you just use the values that I said, I've made it an unforced oscillator. And because I wanted it to converge in a simple way to limit cycles, and this one spirals out and eventually becomes this outer trajectory, and this one spirals in and becomes the inner trajectory. So what I did over here was if I run this for these different values, I get these funny curves. There are the two curves, figure 1 and figure 2. And you can see that this is going to be kind of chaotic. And let's see if I can make it more chaotic. So I think to make it really weird is I'd increase mu, A, and omega. That's the way to really make it crazy. So I'm going to get rid of this 0, and I'm going to make A equal to maybe 3, and this omega maybe I'll set equal to 7, and here maybe 9 and 3.
What happens if you make omega and A smaller rather than bigger? Does it become more?
I think it'd move more slow. It'd look more regular, I think.
Okay.
But you want me to make mu smaller? All right, here, I'll do that. Did you say mu or omega?
Just omega.
All right, so let's make omega smaller in this case.
Just because you made omega bigger in the last one.
Okay.
Just to see.
But I want to make mu bigger, and I'm going to make this equal to 7, say. Okay. All right, now let's also, I think I need to have it run T-span. I'll have it run somewhat longer. So 20,000 in both cases. So we may have to wait a minute or two here. All right, I'm going to set it to run. Anyway, this is the, and while it's running, I'll just talk. So attractors. Now, Hamilton systems, oh, wow, look at that. Boy, that is, that is really, oh my, all right, so so you see the obvious difference. You let omega be something small, then the omega is the forcing term, and it just forces the thing very, very slowly, whereas here it's forcing it very quickly. And my goodness, look at, let's see if I can make this bigger, see if we can get more definition. Well, that's amazing. It's just hit every point in this area. And
what was the propagated time for? Because it's a lot of overlaps.
yeah, you mean the overlaps are here?
Yeah. Did you like run it for a really long time?
Oh, yeah, you're right. So this is one of the things that's called, let's see, where do a limit cycle. So there's apparently this thing has a limit cycle that I would guess it's probably has a fractal dimension. In other words, because of the finite pixel size, it looks solid. But if we actually looked at it carefully, we'd see it wasn't really solid, but it's very possibly a fractal. That in that case, it would be a strange attractor. But let me go back to this one here and run this faster. So let me put omega equal to 9 here, and oh gosh, I don't know. What was mu? Mu was there. Oh, I don't know. All right, I'm just going to run it like this, and it's going to give us the thing we already saw, but it'll speed up omega, so we'll see more action in the second graph. But you can download these codes, you can then change them, and then you can run them on Matlab. And you know, you may discover something. I'm sure you'll find some things that amuse you, and you may discover something you know, interesting. So, oh wow! So what happens when you do that is you once again get this limit cycle, and as I said, it's yeah, you know what, I think we should do this. I think we should cut this back down to, let's cut it down to 1000 instead and run it and see if we see a little, if it's a little less black. Anyway, nah, it's the same business. So they're both going to. Yeah. Notice that this and that are quite different. Anyway, to get back to basically the chapter here, Hamilton systems evolve in ways that conserve their areas in phase space. That's, you know, phase space is all the Q's, all the P's. So phase space for ordinary three-dimensional space is 6-dimensional. 3 positions, 3 momenta, 6 dimensions. But if you consider an arbitrary system, you have n dimensions, and so you have a 2n dimensional system, and that's the phase space. And the areas in phase space are conserved, but of trajectories, but arbitrary autonomous systems can evolve more generally. And in particular, if the system is dissipative, if there's friction in it, then you can see the phase space is going to shrink. And when they shrink, they typically converge to a point or a set of points, and that thing is called an attractor. And an attractor may be a point of dimension 0, a loop, a limit cycle of dimension 1, a surface of integral dimension, or a fractal, which is a set whose dimension is not an integer. And a fractal attractor is a strange attractor. Now, these guys may be strange attractors. The Lorentz system is quite nice, and you can download the code. It's 3 differential equations, which were originally written down for a system that has something to do with weather. And but I forget what it has to do with what kind of weather. Anyway, Lorentz system is 3 first-order differential equations. The x dot term equation is linear, but these equations are non-linear, x times z, x times y, but they're very simple. And what you get is for example, this very nice butterfly pattern. And this approaches a strange attractor, which has a dimension that's slightly bigger than 2 dimensions. And so that's quite interesting. And there's a Wrassler system, which is again 3 differential equations, rather simple. 2 of them are linear, and only 1 is nonlinear. And it has solutions like this. And when you increase C, I think it's beyond at 5.7 or greater, you then get an attractor that's an infinite set of loops of dimension, fractal dimension. So this again is a strange attractor. Now these are all exhibiting chaos, and Henri Poincaré, this is the same Poincaré family, studied the 3-body problem and found very complicated orbits. As I said, the thing is not soluble, and moreover, it apparently exhibits chaos. And when he studied it, what he found was, and of course he didn't have the advantage that we have of using computers or using Matlab, he found that after a transient period, a classical system assumes one of 4 forms, either periodic, steady or damped, quasi-periodic, in other words, more than 1 frequency, or chaotic. And chaos takes different forms in different dynamical systems, and there's no one definition that's appropriate for all of them. But the basic feature of chaos is that the trajectories, the time evolution of the system is extremely sensitive to initial conditions. And so in other words, if you have 2 different initial conditions, the difference between, or the magnitude of the difference between the 2 initial conditions might be some number here, but after a time t, it grows exponentially. And this lambda is called a Lyapunov exponent. So this is one aspect of, one characteristic of many chaotic systems, namely that the trajectories diverge exponentially from the initial conditions. They magnify the difference. It's a little bit like a war. You start with a small difference of opinion and of injustice, and after a while, you've got World War III. Yeah.
So you had said that some of these dimensions reached like 2.06 or 2.01. How do you have a dimension of 2.01?
Yeah. Okay,
I guess I thought dimensions were always like integer values.
all right, great question. And that was the advance that was made by various mathematicians. And I don't know enough history to know when they made it, but I was about to get to that. Why don't we're kind of out of time, but I'm happy to spend next Monday on the rest of this chapter. And and in the meantime, between now and next Monday, you two can play with Matlab and find things that Matlab can do. You see, it can do a lot more than I do with it. I tend to, my view of using computers is I look at the mathematics, I write a program, I run the program. The Matlab approach is you look at the mathematics, you click on Google, find the Matlab system that solves this particular problem, and you run it, and you don't write anything. And so
Python's the same way.
yeah, so but I haven't done that with Matlab. So I suggest that you guys do that over the next week and find some amusing things that Matlab can do. And then on Monday, I can do the rest of this chapter, which is not that much. And you two can show some things that you've managed to get Matlab to do. I think that would be a good exercise for the two of you, and it'd be educational for all three of us. And remember, these days, when you don't know something, you just Google it, and very quickly, Google will get you. Very often Google will get you the answer. I remember once reading that the guy, one of the people who invented Apple, who started Apple, Steve Jobs, he once said he thought of computers as bicycles for the mind. And that certainly turned out to be true. But let me spend maybe a couple of moments here saying something about what a fractal is, just to skip to that. So let's see, where did I just say what a fractal was? Fractals. So it's a set that has a dimension that's not an integer. And the idea is this: you take the set, and you can imagine that it's some set in 2 dimensions. And you then cover the set with either, well, in 2 dimensions, you'd cover it with little squares of size epsilon. And then you see how many, suppose you take epsilon equal to 0.1, and you might need n of 0.1 boxes, little squares to cover the set. But if you change epsilon to 0.01, you'll need a different number of boxes. You'll need more boxes. And you then take the limit of the log of the number of boxes for squares of size epsilon divided by the log of 1 over epsilon. You take the limit as epsilon goes to 0, and that is the dimension of the set. That is said to be the box counting dimension. And if you just have an interval AB, you can cover it with one segment of length AB, and you find that the dimension is 1. On the other hand, if you take a Cantor set, which is, and let's see, where's the picture of the Cantor set? It's back here. There's the Cantor set. So it's first just the interval 0 to 1, and then it's the interval 0 to 0.3, 0.7 to 1, and then it's these 4, but only 0 to 0.1 and so forth. And you then, well, you can just read this and go through it, and you'll see you get log 2 over log 3, which is the dimension of the Cantor set. And what you see is that it's less than unity because the limit of this thing is, the dimension of this thing is 1, but, and the dimension of this thing was also 1. But the limit of this thing is you just got more and more holes. You see, as you go down here, you lose a third, then you've lost the third, but you lose 2 more ninths. And then you lose less, on and on, you lose more and more of a segment from 0 to 1. And in the limit, what you wind up with is a set that has this dimension that is not even a rational number. All right, so I think maybe the thing to do is to quit now, and we can either meet at Pais next Monday or Zoom again, depending on the weather and what you guys want to do. And we can continue with these, with applications of Matlab and the rest of this chapter. And if you want to throw in another topic, send me an email. So let's see, oh Christ, I forgot to record. Well,
No, I think you said you were recording.
Yeah, it's still recording.
Oh, really? What do you know? All right, so I'm going to stop recording now, and I'll put it on the web and send you the link, but I'm not going to list it because the UNM administration is so gun shy that they're afraid of FERPA, of violating FERPA or getting a lawsuit or something. So
Can't we sign that document, the release form or whatever?
Yeah, but you sent it for that other course. I don't even know if it applies to this course, and we'd need one from Abby also.
Yeah.
I don't know. This is just so damned stupid. I really hate this tendency of the last couple of years in which anything that has any student in it, it gets unlisted. And the result is that all kinds of seminars and colloquia that used to be available for free on YouTube are now dark. And it's just basically turned off the enormous advantage that Google brought us. It's just awful. Anyway, if you want to sign the forms or send me new forms, whatever is necessary, I can, put them on in listed form, and I can probably change the listing on these if you send me the forms. So I'm going to stop now and wish you all a good week. And by the way, we're not out of COVID, and the problem with COVID is that it attacks the brain and the heart as well as other organs. So it's not like a cold. It's much, much worse. And of course, some people, it has very little effect apparently, but other people hits the brain and the heart, and it may even lurk and then come back and hit you. I don't know. I'm not, I don't think anybody knows all the details about this. And then the other thing that is just terrible is this war in Ukraine. And the problem that I see is that we once again have a politician who was an actor, like Ronald Reagan was an actor, Trump was an actor, and now Zelensky was an actor, or is an actor. And these actors have enormous punch in the media. And Zelensky is basically driving the EU and Europe into a war with Russia. And this could be a nuclear war. And I don't think the US and the EU should fight a nuclear war to keep Zelensky in power. I think that's ridiculous, and it's extremely dangerous. And because the the newspapers, the New York Times, the Washington Post, and all the other newspapers just love to display the blood and guts of violence in the war because it sells newspapers and attracts viewers. The newspapers then warp up, what am I trying to say? Excite public sentiment, and people call Congress, and then they call the president, and we're liable to get into a nuclear war with Russia, and we could all be killed just because.
Yeah, let's hope it doesn't come to that.
Yeah, and it's not just that we could be killed. There are 43 million people who depend upon grain from Ukraine and Russia. The supply has been cut off by the war, and there are 43 million people in North Africa and elsewhere in poor countries who are threatened with starvation because of this war. And the economist, the Harvard economist, God, I forget his name. I'm terrible with names. Anyway, Lawrence Summers, he said that he thought more people would die in third world countries of starvation than are killed in the war. Of course, he wasn't assuming it'd go nuclear, but that was 2 or 3 weeks ago, and we're closer to nuclear now. All right, I'll stop talking. Goodbye. Have a nice week.
Goodbye, Professor.
Goodbye.
Goodbye.